Hi everybody. This is Key Assessment 4 feedback, electrons, bonding and structure. Okay, let's go through questions one by one. So question 1 here, options that give the correct electron configuration. You should know that the electrons fill from the lowest energy level out to the highest energy level, and they only pair up when they have to. So obviously you need to, I suppose here, you can see straight away that that one is incorrect because you should have an electron in the final box. Here looks okay. This one's definitely not okay because there's no other electron in the 2s subshell. And this one could be okay. So you're looking at those two. This one's got 7 electrons, which is nitrogen. This one has got 2, 4, 6, 6 electrons, and boron only has 5. Okay, so obviously, you should be able to whiz through that in your head quickly, looking at the periodic table. The following statements about hydrogen selenide. It's in the same group as oxygen, so should know straight away that it has 2 lone pairs. So it will have a higher boiling point than hydrogen sulfide. It's not linear. There is not one lone pair, and it cannot form hydrogen bonds, so it has to be this statement, doesn't it? It's a higher boiling point than hydrogen sulfide, and I would put that down personally to the instantaneous dipole interaction because it's got more electrons than sulfur selenide, selenium rather, selenide. Okay, question 3, potassium oxide has a melting point. You're given some information there about 2 different compounds, and you're asked to establish from the table which 2, are correct. Is K2O ionic? Is SiO2 metallic? Well, K2O is ionic, but SiO2 is not metallic. Go through the pairs and you find that K2O is ionic, and SiO2 must be giant covalent because of the enormous melting point. Yeah, so it's covalent because they're both non-metals, but it can't be a simple molecule, so it wouldn't have a melting point that high. Okay, question 4. Which of the following does not have a trigonal pyramidal shape? Which means if it's trigonal pyramidal, it means there must be lone pairs, yeah, because it squashes the bond angles together. So these have all got lone pairs apart from boron, which has 3 electrons in its outer shell, so it's just forming the 3 bonds required. Okay, so you're given some electronegativity values in question 5. Asked to define the term electronegativity, and a number of you missed out a really crucial piece of information. It is the ability of an atom to attract the bonding pair of electrons in a covalent bond. Okay, very important. I've spelt covalent incorrectly there, by the way. That should be an A. I don't know what I was thinking. Okay, how does electronegativity give rise to permanent dipole-dipole interactions? And a number of you totally missed the point of this question and didn't mention electronegativity. Obviously, you've just defined electronegativity. These 2 questions, they kind of go together. You've defined it. Can you apply that definition now? So if there is a higher electronegativity in a bond, one of the atoms has got a higher electronegativity, the electron density in that bond will obviously move towards the more electronegative atom, making the bond polar. So they're the 2 crucial ideas that should have been in that answer. Use the information to name all the intermolecular forces in each of the following compounds. So HCl, so this is all the intermolecular forces. Quite often they just say the strongest intermolecular force. So if this is polar, HCl, we know it's a permanent dipole-dipole, but there will also be London forces acting. Yeah, they act in everything. Okay. Oh, I think I've put this the wrong way around. Yeah, sorry. I'll go back to that other page in a minute. I must have, when I was scanning, I made a mistake. Okay, so CH4 just has London forces, nothing else. The bonds are not polar, and the overall molecule is not polar. And HF, of course, for fluorine, is one of the 3 electronegative atoms, so it participates in hydrogen bonding. Also permanent dipole-dipole interaction, because hydrogen bonding is a special case of that. And as I said, London forces act in everything. Okay, draw a diagram to show the strongest intermolecular force between HF molecules. Now, I've shown this to you on the board numerous times and stressed to you what you need to include on the diagram to get your full 3 marks. And this should be probably the easiest 3 marks on the paper. Yeah, you've got to show the bond between hydrogen and fluorine. You have to show the partial charges. You show, or it even says in the question, all the lone pairs. Loads of you didn't put the lone pairs in. And then you show the hydrogen bond from the lone pair to the hydrogen. You do that, you get 3 marks. And it probably takes about 45 seconds to draw. So that's probably the easiest 3 marks ever. And then explain why the only forces between chlorine molecules are induced dipole-dipole interactions. Again, this question is all about electronegativity. So, you know, the questions kind of follow on from each other. And a number of you didn't seem to recognize this, that the reason, explain why chlorine molecules only have London forces or induced dipole, is because there is no difference in electronegativity, so we don't have a polar bond. And the electronegativity is the concept that is most important when we're talking about intermolecular forces. Okay, so focus on electronegativity whenever intermolecular forces come up. Question 6, calcium is an element that can react to form ionic bonds with negatively charged ions. Calcium oxide, state what is meant by the term ionic bond. That's just a straightforward definition, and I'm glad to say I think everybody in the class got that correct. Right, I need to go back up here to finish this question, don't I? Yeah. So we're given the electronic configuration, asked to give the electronic configuration of the calcium ion, which is 2+, which means it's lost 2 electrons. So it's straightforward. Once you recognise, you just have to write an electron configuration with 18 electrons in it. Dot and cross diagram to show the bonding in calcium oxide. Show the outer electrons only. Now, you could have put 8 electrons in here, which would have indicated, you know, that the outer 2 electrons have gone. It wouldn't have mattered if you did. But you definitely needed to show the 2 electrons here that have come from calcium. So the 6 crosses are the oxygen electrons, the 2 dots are from calcium, and you must put the charges in, okay, and the square brackets, okay. It can also form the ionic compound, okay. So there's a bit of information there that's just telling you, but the crucial thing is this question is about carbon dioxide, isn't it? So state the shape and bond angle of a molecule of carbon dioxide and explain the shape. Okay, so easiest way to state the shape and bond angle is to quickly draw it out, give the shape and the bond angle. Okay, and then to explain it, there are no lone pairs here, so there's no kind of extra repulsion force. So therefore, the bonding pairs repel each other as much as possible, and those words will pretty much need to go into any question that asks you about the shape of a molecule. Why it takes up the shape it does, it will be because bonding pairs repel each other as much as possible, and lone pairs repel a little bit more than bonding pairs. Okay, but there aren't any lone pairs here, so we get the straight 180 degrees. Okay, looking at calcium oxide and carbon dioxide together here, being asked about higher boiling point. Now, if you don't recognise straight away that carbon dioxide is a simple molecule, and you think that covalent bonds are broken when we break when we boil substances that have simple molecules, then you are completely wrong, and you really need to focus on that. Your understanding of simple molecular structures and the bonds that are broken when they are boiled. It is not the covalent bond. It is never the covalent bond in a simple molecule. Refer to water in your head and think what comes out of your kettle when you boil it. Okay, so calcium oxide, you have to obviously recognise that's ionic. It's going to have a much higher boiling point than CO2 because you are only breaking the London forces in CO2. You are breaking the ionic bonds in calcium oxide. Okay, done that one. Right, okay, so question 7. Okay, so you're given a graph showing you boiling points of some group 5 hydrides, i.e. hydride is the element just bonded to hydrogen. And then it asks you to explain the trend in boiling points shown by the graph for the group 5 hydrides. So first thing is you have to recognise what the trend actually is. Now, as we can see, the trend here is that the boiling point is increasing as we go from phosphorus hydride to, oh, I can't remember what that is, SbH3. Okay, the trend is increasing, but you notice that NH3 is not following that trend. We would expect the boiling point to be down here, wouldn't we? If the trend was being followed, we would expect it to be here, but it isn't, it's higher. So that is going to be a crucial question that you need to address. So, what is the trend? There is an increase in boiling point from pH3 to SbH3, but NH3 doesn't follow the trend. You know, state that. And then, why? pH3 to SbH3, number of electrons are increasing, so the London forces are getting stronger and it takes more energy to break them. So it's recognising that London forces obviously are acting here. However, NH3 can form hydrogen bonds as well as London forces, and it takes much more energy to break hydrogen bonds than it does to break London forces. So you need to approach this question in a very methodical way. First of all, state the trend, state what doesn't follow the trend, and then explain your observations. Shape of a molecule of pH3, labelling the size of the bond angle as well. This is it's got 5 electrons in group 5. It's making 3 bonds, so it must have a lone pair. So it's 4 lots of pairs of electrons around the central atom, but one of them is a lone pair. So we're squashed in from our tetrahedral 109.5 to 107 degrees. Why is ammonia the most soluble of the group 5? It can hydrogen bond with water. It's a straightforward answer there. Okay, question 8. So it tells you about bonding of fluorine and sulfur to produce the molecule SF6 and the molecule BF3. Okay, so it asks you for a dot and cross diagram, so there we are, pretty straightforward, 6 fluorines around the sulfur atom. To explain the shape of the molecule, again you're explaining the shape, alright, so the explanation is that you've got 6 bonding pairs and they all repel each other equally and they form an octahedral shape with a bond angle of 90 degrees. Okay, fluorine ion can react with BO3 to form BF4 minus ion, and a dative covalent bond forms between them. So the bond angle in BF3 is 120 degrees, not trigonal planar. I mean, it doesn't ask for the shape. I've written that there just to remind you that that's what the bond angle is in a trigonal planar molecule. Definition of a dative covalent bond, you know, both of the bonding pair of electrons coming from one atom. And then finally, a dot and cross diagram to show the bonding in a BF4 minus ion, and your diagram showing the outer electrons only. So we need to show our 4 fluorines and our boron in the middle. We need to show our 3 electrons from boron, which are crosses. We've got the dots are from fluorine, And here, obviously, we've got the dated bond, haven't we? Where fluorine is donating both electrons. It's a minus ion, so there must be an extra electron in there. So, yeah. So this has got 8 electrons rather than 7. Otherwise, it wouldn't be minus. And don't forget that you have to show an ion with square brackets and the charge. And then we're just asked about the shape. So we've got 4 bonding pairs around the central atom. So it will take up a straightforward tetrahedral shape. There are no lone pairs. And all bonding pairs repel each other equally. Again, to get that extra mark, you needed to say that. Okay, so well done, everyone. We've got through another KA. I'll see you all soon. Bye.